With that, let me share my screen, and that way we can actually get started. Um, Give me just a second. All right. So before we start, I think Sahana, as Sahana briefly provide my introduction, and I was very excited to meet you all here. I mean, virtually though. Hopefully in the future I'll see you guys in person. But I'm based in San Diego, California. Here, it's night, but I'm so excited to see you. With all my excitement. Today we are going to talk about a semiconductor, um, and why semiconductor is so important today. What's the importance of it? What is semiconductor? How is it going to be game changer for your career development, and what are the skill set that you might require, and stuff like that, right? So with that, without actually taking a lot of time about going here and there, I'm going to start presenting the presentation that I have it for you guys. And let me share my screen. Um, all right, let me know if you guys see my screen. Sana, is it visible?
It's yet to come up. Yes, it is visible.
It is visible. Perfect. Okay, so with that, let's get started. So my name is Ankit Gopani, and as I said, I'm based in California here. And you can go to my website to know just to if somebody is interested to see who am I. All my information is in my website. Website link is here. So today we are going to um, cover a couple of important items in this webinar. So first of all, why semiconductor, right? So I'm going to touch up, we all talk about semiconductor these days. Everywhere we see that, people are talking about semiconductor chips, SoC, ASICs. These are all very, known words these days because everything is digitalizing, right? So and what is semiconductor is also something I would like to touch to give you guys an perspective about, what does it mean, right? And then I will take you and walk you through the chip development process, including the front end, back end, and manufacturing process. So I'll just walk you through to give you an idea about, what does the chip development process with respect to different stages, what each stages does, and then things like that. Then we will also cover the semiconductor ecosystem, which also includes, all of the different partners and all of the different companies associated and building this whole ecosystem, right? Which includes, and we will go over all the categories, in this presentation. We will also talk about the important skills with respect to industry need, right? So this is something give you guys an idea about, where you can focus depending on your interest and your choice of interest within this, chip development process. Okay. And then given a time, we will also, try to address questions and, we will try to address some of your questions. Okay. So why semiconductor, right? So just at the high level, today, if you see, everything is digitalizing, right? Everywhere you see, the semiconductor is future basically, and it's everywhere, right? You talk about any component or any business segments. We talk about aeroplane, we talk about autonomous car, we talk about smartphones or any device, electronics device today, right? We go to hospitals and you see a lot of different digital machines, right? And you see artificial intelligence. Everywhere you think about, there is a chip, associated with it, right? Which means digital electronics is everywhere, right? So, and that is why it's actually becoming more and more important day by day, right? I mean, if we talk about 10 years or probably a few years ago, nobody knew that, we will be switching on and off our lights by just giving a command, right? Like today we just say, hey Google or hey Alexa, switch on my light. I have everything set it up at my home. So my son and family members usually don't switch on, turn it on and turn it off. They just give command to the device, right? And it controls your lot of lights and a lot of different functionality, right? So all of these functionalities, if you see, it's all about the connectivity, and connectivity happens through this digitalization format and the chips and the digital electronics. Okay, so thinking at the higher perspective, any segment we talk about, either it could be automotive, it could be Internet of Things, it is like artificial intelligence, machine learning, a computer vision, which includes the camera, or all any type of things, right? Camera can be in your smartphone or in your laptop, in your, holding the SLR camera on your hand. Any digital device we talk about has a chip. It could be less or more complex chips depending on its functionality. Okay, so I'm just giving you an idea that why we are talking about semiconductor today, and why it is actually getting more and more importance day by day, right? So there is a market study which says that global semiconductor market forecast to grow, and it is going to reach $900 billion in by 2027. So this is a huge opportunity, and this is the next growth segment if we talk about, right? So there is a huge amount of opportunity for all engineers who would like to solve problem, right? So problem solving skill is very, very important. And we all are engineers. I was one of them 20 years ago, sitting in the one of the benches like you guys are sitting, right? So I can absolutely understand how you guys are going through your educational cycle, and and you guys must be excited to come out in the industry to make your career, right? So I'm going to help you guys to just, stimulate some of the thought process in your mind so that you can actually make a better decision. Okay. So opportunities point of view, if you see, there is a huge demand for semiconductor resources in all stages of chip development. Okay, including EDA tool experts. And I'll talk about what does that mean. Okay, so one more perspective, just to throw in another thought process, is chip development is very complex process, right? As I said, engineers needs to be having a conceptual stuff, that the problem solving skill is a very important skills, and we will touch up in the later slides. So, and the complexity is growing exponentially, right? We are talking about billions and billions of transistor in one small package, right? I mean, I don't know if you guys have seen, if you guys have seen about the any of the processor or any of the chip, right? Probably you guys might have, some, we are all engineers, so I mean, some of you might have picked up the screwdriver and opened up your smartphone which is not working, and try to see what all electronics that does it contain, right? So you might have seen some of the chip, right? So, and for an example, if you see the Apple recently came up with their M1 processor, which single chip processor has 114 billion transistor in that small chipset. Okay, so just to give you an idea that how complex would it be in terms of the digital electronics, that we are fitting more and more transistor in a smaller size of the chip, right? So NVIDIA's another example is NVIDIA's A100, which is a GPU processor which has 54 billion transistor in one single package. And we are not ending there. You know, there are some companies in the world which are working to accommodate trillions of transistor in single package. Yeah, I mean, you would be surprised, but yes, this is what the complexity growing exponentially, right? So let's jump into the further more detail, that now that we kind of try to understand why semiconductor, let's also try to understand what is it, right? Because you guys probably more excited to see what is semiconductor. Okay, so let's see. So this is pretty simple, right? Everybody knows about conductor, right? I mean, this is like a physics, right? So the material that allow current to flow is a conductor, right? So for example, gold or copper or iron or aluminum, these are all metals, right? Through which electricity or the conductivity can pass, meaning the current can flow through. So these are the materials that we call it as a conductor. Okay. Similarly, there is, you guys know, insulator, right? Rubber, plastic, wood. These are all materials through which current cannot pass through. So these are the stuff that we call it as an insulator. Now semiconductors, fit in between, right? So semiconductor is like sometime it has conductivity, sometime it doesn't, right? So now how do we make such material? So there is a process involved to it, right? So, and we will understand. So basically, when you inject the impurity, when I say impurity, meaning, and I'll talk more about it. So when you inject an impurity, that we call it as a doping process. Okay. By injecting an impurity, we make semiconductor material, which will be used in chip development cycle. Okay. So I know this is probably a heavy word for you, but I just hold your thought process. We have a lot of different, material that we need to go through. A lot of your things will be addressed as and when we go forward. But if you have questions or something, please keep a note in your notepad. We will discuss, give a time to, go over the question and answer at the last. Okay. So now, giving you more perspective on it, that and again, I'm kind of touching some of the items from the physics, right? Because we need to really understand to be able to get an idea what the semiconductor is. Now if you recall that the physics, right, which is a periodic table, right? So silicon is actually the 15th group of the periodic table, a 14th group of the periodic table, right? I'm actually marking it here through a laser light, so you guys all can probably see, So by default, if you see the characteristic of the silicon, this particular element itself, it has four outer electrons, right? Which means no free charge carriers with the four electrons. As a result, pure silicon is absolutely non-conductive at room temperature. Okay, so when somebody says that pure silicon, can it carry a current, you can pass through a current? No, it's absolutely non-conductive at room temperature, right? So which means, how do we make it conductive? Right? So to make it conductive, you need to come up with an impurity. You need to inject other elements so that the electron structure would change, right? So scientists identify all these years that phosphorus and boron, which you, if you can see, is the element from 13th and 15th, a group of the periodic table, are the best suitable element, because phosphorus has one extra electron which can move freely when inserted as impurity. Now you would see, what we are injecting impurity here. So in example like phosphorus, when you inject a phosphorus, right, as an impurity to the silicon, which creates the n conductive material, right? Because phosphorus, if you see, has an extra electron in this figure, if you see, which can actually freely, flows through as a part of initiating the conductivity. Right. Similarly, boron has one less electron, right, which creates the holes and which can move as positively charged particle. Right. So that way, depending on what type of impurities you add, semiconductor materials are getting generated accordingly. Right now, you have heard about the NPN transistor and PNP transistor, right? So you can easily correlate this fundamental structure. What is NPN transistor and what is PNP transistor? It all depends on what type of impurities that you are adding into the semiconductor material to be able to use it for your chip development cycle. Okay, I hope you all are with me so far. A little more detail about the semiconductor. What is it? So um, the right hand side of the figure is very familiar for you guys because during the educational process, we all experiment with this type of transistor figures. And in fact, you guys might have used the circuit board and put together transistor resistors and things like that to make some sort of a circuit in your some of the projects, right? So in some of your books, you might have heard about, what is the PNP transistor and what is NPN transistor, right? But I'm not going to go into detail that much because you all know, reading from your books and things like that. But what I'm trying to highlight here is that similar transistor property, how we are, developing in the fabrication plant or the chip manufacturing process, right? So actually, if you see in detail, the transistor are being, made by creating the, silicon oxide and conductive polysilicon layer, right? So, so polysilicon conductive layer on top of the conductivity, which will control the transistor property. So transistor is nothing but a switch, right? On and off type of stuff, right? So, so here when you add an additional charge to conductive material, which is this, right? The moment you add the charge here, the electron starts traversing through N to P to N material, right? Which is how the current starts flowing through, which means the circuit is actually closing, right? So closed circuit to pass the current. So that's how the current is actually getting transferred. The moment you stop the charge, it will stop flowing the electron through, right? That means that circuit is turned off or the switch is off. Okay, so that is the transistor characteristic. Now, why we are talking lots of things about transistor? Because transistors are the smallest control unit of chip development. It's all about transistors. Any digital functional or any digital technology that we developed is eventually is gonna turn up into the number of transistor to form a one big circuitry, okay, which we call it in a complex term, or which we call it in a another term is a system on chip or ASIC, application specific integrated circuit. Okay, now when was the first transistor invented? The world's first semiconductor, the transistor, invented by Bell Laboratory in 1947, the same year of as when we got independent, right? So, so yeah, since then it's I mean the engineers or scientists never look back. I mean the complexity keeps growing, and today you see, right, a lot of complex digital electronics in front of us. Okay. So now, high level, again, I'm not gonna go into details. I know you guys probably might not have that much, I don't want to keep getting bored by going over a lot of complex terminology here, but at a high level, giving you an idea, right? When you see a you know when you see any digital circuit or any digital chip in front of you, think about this. How would it been developed? What was the development cycle when somebody started developing the chip? What all different cycles that needs to be done to be able to develop that chip, right? So chip is basically the very first, or the raw material to develop the chip is nothing but a sand, because sand has a silicon substance or the silicon material, right? So through a lot of different processes from sand, um, we extract the silicon material of it, and then from silicon, through a lot of different process, we develop the ingot. This is called, this is called an ingot. Ingot is nothing but actual silicon material through which you are then eventually you will keep slicing this ingot to make a different fabrication wafers, right? So these are all wafers, and on this wafer, when you imprint the circuit, that's when the one particular chip develops. Okay. So like if you see here in this big wafer, right? And if we are developing, if we have developed a processor, for example, as an engineer, now I have a layout and processor circuitry in my GDS2 or, in a format, right? Then when through different process and the machinery, when you imprint that circuit into this wafer, that creates the chip. And then that chip will actually be packaged together and put it in a system where you would like to be used. Okay, so that is a high level process. So we call it as a sand to silicon, meaning silicon chip, right? So raw material is sand and the end material is actually your chip, which we are using it in any digital device. Okay. Now you might, come up with a question, I mean, with a thought process that why this is in circular or the round shape, and I guess the answer resides just right here because through process, the making of ingot process is always in a circular form, meaning the ingot is always be in this shape, right? So so when you slice those ingot, it will be in a circular um, shape, right? So and just to give you an idea, I just put a small picture here to get you an idea that if you see a small square blocks here are nothing but represents one SoC or one chip, which can be very complicated. And as we saw, each one of these chip can contain billions of transistors. Okay, so that's the complexity of it. Okay. um uh, Everybody are with me so far, I hope. Okay. And going to the next slide, uh, giving you guys even more details, and with some sort of an historical stuff is that when was the transistor, born? I mean, we just saw it was in 1947, right? And then if you see the Intel developed their, one of the first CPU, central processing unit, in 1971, which had 2,250 transistors only. That CPU had only 2050 transistors in one package. And that was when? 1971. Since then, look at the complexity that engineers and industry have, solved. And now today we are talking about trillions of transistor in one package, right? So that is what the engineers are doing. And in future, some of you guys might be doing the similar thing, talking about even more complexity in the future. Okay, so one more thing I wanted to give you an idea that a lot of people talk about the different nanometer technology that some of the chips are getting developed in 65 nanometer technology. Some of the chips are getting developed in 28 nanometer technology, likewise 7 nanometer, 5 nanometer. We are talking about even 2 nanometer these days. We don't want to get into that much detail, but give you a perspective of it is, 1 nanometer is 1 billionth of a meter. Okay. So it's that small. We can't even, I mean, it can't be visible through a human eye. I mean, we can't even see that in stuff, right? So, you know what? Give you one more perspective. So when we talk about somebody, if you heard about that, somebody is developing 10 nanometer chip, which I have worked in my past, and currently I'm working on even advanced nanometer chip technology these days. But 10 nanometer chip is, it is what is one 10,000th of human hair, which means our hairs 10,000 pieces you make, it is that much thin. Okay, and that is why we are able to, I mean, it is that complex, which means, when you create a transistor, through that process, so the physical dimension of that transistor is 10 nanometer, which is 10,000 smaller than your human hair. It's that thin. And I'm just talking about 10 nanometer technology. Industry already working on 7 nanometer, 5 nanometer, and even 2 nanometer further down. If you just do Google, you would see, right? So think about you know, the complexity. And we will touch up, why we are heading that much complex technology node, because there are benefit of it. Okay. So as Sahana mentioned at the beginning, I just wanted to give you guys some opportunity to see. So far, we have learned about why semiconductor, what is semiconductor. At least I've tried to walk you through, right? To see, I mean, if any one of you has remembered, what was world's first semiconductor and who invented it, right? So maybe it's a time to win your surprise, as Sahana mentioned. So anyone wants to answer this question, just raise your hand. I guess somebody will just check to see. Maybe Meghna, ma'am, or anyone there can help.
Meghna, can you unmute your laptop?
Yes, ma'am. Can you able to hear me?
Yes,
Yep.
we are able to hear you.
Just a second. I'll hand
So
over the mic.
yeah, and don't feel shy. Anyone, anybody, please don't feel shy. Even if you answer wrong, absolutely fine. I was one of you, sitting all the way on the last bench. What was it, Meghna?
Have you heard, sir?
No,
Hello.
I mean you can repeat. Maybe I can hear you nicely, maybe, but I didn't hear that clear. A little bit, but it's okay. You can answer yourself. Maybe
Now is it better?
yeah, it's better.
Oh, okay. So the first semiconductor was galena crystal invented by Sir Jagdish Chandra.
Okay. So actually, the first semiconductor was invented. I mean, first semiconductor was nothing but a transistor, which was invented in 1947 by
As
Bell
per
Laboratory.
records, it was Walden and Shockley who invented in the Bell Laboratories in 1947.
Correct.
But according to, I think, we know the wiki also it is recorded that galena crystal was the first semiconductor invented by Sir Jagdish Chandra.
Absolutely. That information is also true. Cool. So we can, yeah. What? Awesome. Great. Cool. Very nice. Um, and the second thing we just saw, so 10 nanometer chip circuit lines are how thin in comparison to human hair. We just talked about it, right? I mean, when we talk about 10 nanometer, transistor dimension or the technology with respect to our human hair, how thin is it? Anyone? Okay, no, that's okay. I'll just keep going. There is no one, but it's basically 10,000 times thinner than the human hair. Okay. All right. So are you guys all with me so far? I just wanted to see your thumbs up. Yeah, that makes me feel better. Awesome. Okay. I hope I'm not getting you bored, but these are all very useful and important stuff that I would like to just throw my knowledge to you, so it will be helpful for you to make decision in your career. And you can always, approach me too, when I'll provide my contact information. But moving forward, now we are entering into very interesting topic to understand the chip development cycle. Okay. So I'm going to touch on, I'm going to try to touch upon um, each and every, at high level, each and every phases of the chip development cycle. Okay. So before we go there, let's understand what is ASIC and what is SoC. Okay. So ASIC is nothing but an application specific integrated circuit, and SoC is nothing but a system on chip. Okay, so the key difference between both of these is ASIC is a chip that is custom designed for a specific application. As a result, we call it as an application specific IC. Okay, and SoC is nothing but a complex IC that integrates major functional elements into one single package. We call it as a system on chip, the whole system on chip. Okay. So both of them are kind of, it's very popular these days, depending on the different applications and different need, industry develops such stuff, right? So one of the examples for ASIC component is a 24 cross 24 10 gigabytes of Ethernet switch, which is kind of a custom design for specific system to meet the performance, right? For certain data transfer at a rate of certain speed, there is always a customized need for some of the companies. As a result, they develop certain customized application specific ICs, right? Similarly, for system on chip, if you see, I mean, this is something we see, in a regular life, like mobile SoC, right? Snapdragon processor, Intel processor in the laptop, like i5, i7, or i3, Pentium 3, whatever different processors that we have heard, right? Those are all, we call it as an SoC, right? Because it consists of a lot of different components into one single package. Okay, so that's about the ASIC and the SoC. Now let's understand the chip development process at high level. Okay, so everything starts from the system specification and architecture, right? If you want to develop something, right? I mean, say for example, I mean, just to give you a higher level perspective, that if you want to if you are a construction engineer or a civil engineer, if you know that you want to develop a maybe 10-story building, but then you have to identify how you're going to build. You have to make a plan, put together stuff on the paper, then think about it, architect it, design it, and stuff like that, right? Similarly, when you develop, or when you want to develop some chip, the system specification and architectural design is the very first thing. You put together a specification, you put together the block diagram, right? That what all different components that you would use and things like that, right? Again, these are all high level stuff. I mean, we can actually talk about hours and hours for one particular segment of it. But just to give you a high level information, very first phase is system specification and architectural design. Okay. The second phase is, once your system specification and architectural design is done, one has to start writing the functional, or we called it as a RTL design, right? um and the logic verification. So these days there is a, I don't know if you guys have exposed to Verilog or any of the VHDL type of hardware descriptive languages. But if not, you would probably in future would see, and if yes, then you know what am I talking about the RTL design. So VHDL and Verilog type of a languages, you put together your logic information in in a form of, some sort of a language perspective, right? So it is a hardware descriptive language, right? So if you want to design, say, for example, 2-bit um, counter, digital counter, then you just write a Verilog code, right, which behaves like a 2-bit counter with required input and output, right? So those are the things we call it as a RTL design. Okay. So once you design your RTL, you also need to make sure that whatever you design is going to work correctly, right? So there is a verification also that is involved here. Okay. So here in this phase, you do the RTL design and you also do a verification of that design. Okay. Once that is done, you basically now that your Verilog code is designed, verify, and then you run the synthesis tools, right? Synthesis meaning you are converting your hardware descriptive language into a digital gates. Okay, so when you provide hardware descriptive language program into a tool, it will give you this type of gate design. Okay. And this is probably is very familiar to you guys because in digital electronics, you would probably see NAND gate, AND gate, XOR, NOR, all those different gates to perform certain functionality of it, right? Adder, subtractor, and the different types of thing. But any digital operation or the performance or the functionality is achieved by, developing the HDL code and converting into a gate level design, right? And then you do the physical design and verification to make sure that your timings, your clock trees, and all of those things are being taken care the way it should be. Okay. So that is the phase we call it as a physical design and verification. Now the next phase is once that is done, right? Which means when your graphical design format, binary format file is generated, which has all the information of your design, your timing constraint, your foundry information, all of those things, then you give that GDS2 file to the fabrication company, meaning the foundry, right? Who actually manufactures the chip, right? Then it will just use that file as an input and manufactures the chip on the wafers that we saw, right? Once the chip is developed, it's just developed, right? I mean that you have a chip and that chip is being used in any of your, digital electronics like this, right? So, and that is how the actually whole process works all the way from specification to your final product, right? So these are high level stages that, one has to go through to be able to develop the chip today. Okay. So let's go next. Further more detail into the, little more details, right? About what all stages does one needs to go through. And remember, this particular diagram or a slide will give you an idea that what all different stages of the chip development cycles are there. And depending on your interest, you can actually start thinking that I like this particular stage of the development cycle. You can think about it to see how you can develop the career around that cycle and stuff like that, right? So I'll just go over it. um let's see. So if you see start to finish, right, there are three main phases of the chip development cycle. One we call it as a front end, one we call it as a back end process, and the last one we call it as a fabrication, test, and assembly a process. Okay, before the chip actually considered to be as a final product development. Okay, so now let's understand what does the front end consist in this verification process, in this chip development process. So front end has these all different stages. Okay, as we saw before, it all starts with system design and architecture. specification document, which means you put together your requirement. Okay, I need 5 gigabytes or 5 megahertz of clock frequency, for example. I need to transfer my data at this rate. Okay, all of those such requirements you put together in a specification document. And from that document, engineer would start writing the RTL design in Verilog or VHDL, one of these language. Okay, so that's the RTL design. Now, RTL design, after this, I mean, in parallel, the verification engineer can start writing the verification program to make sure whatever RTL design have been written is actually functionally working correctly or not. Okay, by writing the test cases, by developing the test environment and things like that. Okay, so these two phases goes in parallel, and these two phases are, I would say is most, I mean, if not the most, but one of the most demanding, um, you know, skill set in the industry today. So my expertise all these years, most of the time I have spent my time in these two phases. Okay, in my career. So I started with this, but because over the years I've worked with many different companies, I got an opportunity to touch up a lot of different cycles to the chip development process. But here is where I actually spend most of my time in my career. And this is very crucial process. And the reason is, if you forget to verify some of the functionality here, and if with that bug, if you continue developing the whole cycle, and if chip gets developed and if it goes in market, and then you identify a bug, right? Then millions of dollars would go west, right? Because hardware cannot get changed. It has to go and redevelop the whole cycle, right? If you're using a phone today, for example, and if you see that the chip is functionally not working correctly, I mean, that chip is if it identifies that that chip has a known bug, then that chip is actually of no use for that particular functionality. Either they have to disable it or they have to redevelop it, right? So it's not like one of those things in software that you identify bug, where actually you can just modify a program, put a patch or a fix, and make a new release, and you use the new software. It's not like that in hardware, right? So that's why it's very, very crucial and very important stage in the chip development cycle. Okay, give me just a second. I'll just take a. Okay, so moving forward, after this design and verification is done, one basically do the synthesis to check to see, you know, my developed RTL has developed how many gates of design, right? Say for example, you wrote a, 4-bit counter in Verilog code. Now, when you run that 4-bit counter program and run a synthesis, and you identify that, you know, there are it has developed, say it came up with say 150 gates of design, then you know that okay, to achieve my 4-bit counter functionality, it is going to take or consume 150 gates. Okay, so that is how you actually come up with an detailed um, detailed information about the logic synthesis, and that creates the netlist. So this whole process, we call it as a front end um, phase of the chip development cycle. Okay, once that's done, we move to the backend process, and backend process is also another another complex process, and one of the a very important process in the chip development cycle, because this is where you actually partitions the design, which means, say for example, let me give you an example here, that in one of the processor, let's say one of the processor you are you are architecting and you developed all of those things, and processor has central processing unit, different components that they it has some sort of a cache memory, and different components, right, that you define, right? Some of the input output, meaning we call it as an IO and stuff like that. Now, when you do design partitioning, and floor planning, it needs to identify that, all of the sub-component within the processor, if two components are talking to each other more frequently than other, they need to put together closer, so that the architectural point of view, it doesn't require the long circuitry lines, meaning the wires, right? The longer the path, the you see the less performance, because the electric or the electron has to traverse through longer than shorter, depending on how you have foreplanned and architected those stuff. Okay, so here we are actually making sure intelligently and optimizing all of the blocks to make sure that in a small place of the given die size, meaning the size of the chip, how you can fit together optimally all the components from your architecture. Okay, that's what actually in this backend process you do in the floor planning and placement. So in placement also, put together all the components optimally closer to each other, depending on how they are communicating to each other, right? And then the clock tree synthesis is nothing but a clock tree schemes. There are different types of scheme depending on your applications of the chip. You use certain type of a scheme. We don't want to get into too much detail.